It's a 100,000-ton steel behemoth, longer than 3 football fields, brimming with jet fuel, missiles, nuclear reactors, and over 5,000 human beings. Now imagine it lurching in 25-foot waves, the deck pitching like a carnival ride, jet engines screaming, alarms blaring, and you're not a visitor. You live here. You work here. You are responsible for making sure it doesn't all go wrong. Welcome to life aboard the USS Gerald R. Ford. This isn't just a warship. It's a moving steel city, and surviving, let alone operating efficiently inside it during violent sea states, requires something beyond raw skill. It takes relentless training, brutal realism, and engineered resilience. Sailors don't just join this environment, they're forged by it. The ocean doesn't care about schedules, and there's no pause button in the middle of the Atlantic. This chaos is the default, and preparedness isn't optional. It's the only line between mission success and catastrophe. Training begins long before sailors step onto the flight deck, immersing them in rigorous simulated environments where ship handling, emergency communications, and flight operations are obsessively repeated. In high-fidelity bridge simulators, teams coordinate in split-second crisis scenarios, facing simulated wind shear, power outages, and rogue wave events. These aren't just drills. They are engineered stress tests designed to burn correct responses into muscle memory before adrenaline takes over. When your job is to launch a $120 million aircraft from a moving runway in a typhoon, freaking out isn't in the manual. Their sophisticated radar, tuned to detect the known, is deaf to the inevitable. On board, the ship itself becomes a proving ground where drills are sudden and without warning. Fire on the mess deck, gas leak in engineering, or unexploded ordnance on the flight line. General quarters means a full ship lockdown, and everyone reports to their emergency station to simulate the absolute worst. The physicality is non-negotiable. Firefighting in full gear while the ship lurches violently is simply Wednesday. On older carriers, tragic explosions have shown the cost of lapses in readiness. The Navy learned the hard way, and now the motto is clear: train like you're already at war. The USS Gerald R. Ford's crew internalizes crisis management until it becomes instinct. What took them years to bury took seconds to exhume. Training follows a deliberate gradient of complexity. First, basic orientation. What to do if the lights fail, where to run if the hull breaches. Then, watch standing in controlled environments, learning communications protocols and basic aircraft handling. Next, intermediate-level operations with limited aircraft and standard sea conditions. Only after proving steady nerves and consistent execution do sailors enter the final layer: high-stakes scenarios in unpredictable sea states. Flight operations in rough seas are the ultimate challenge, placing sailors 20 feet from a jet engine on a moving deck in rain and 60-knot winds. But by then, they're ready, systematically hardened to handle it, making their confidence built on years of training, not hope.
Before we get to that, I need your help. I'm trying to hit 50,000 subscribers by the end of the year, and I need your help. So I would really appreciate it if you could subscribe and help me out.
Fatigue is a mission risk multiplier. The USS Gerald R. Ford integrates crew endurance and fatigue management protocols at every level. Sleep cycles are analyzed, and watch rotations are carefully calculated to match natural circadian rhythms. Lighting on the ship is modified to reduce sleep disruption, and commanders monitor cognitive degradation because one bad call can cascade into disaster. A Navy study showed sailors deprived of sleep for over 36 hours had cognitive function comparable to a 0.10 blood alcohol level. The ship cannot afford impaired minds navigating nuclear reactors or controlling flight operations. Leadership is the glue. Senior officers engage, embedding themselves in the same routines as junior sailors to build accountability and cohesion. If the executive officer can hold a fire hose in a blackout drill, so can you. In real-world missions, a leader's confidence, presence, and experience act as psychological ballast when fear or doubt creeps in. This is mission command in its rawest form. Lead by proximity, command by example. Rough seas are not just background noise, they are a constant and lethal variable on the flight deck. Flight deck personnel undergo specialized physical conditioning, training to move with the ship, not against it. Safety harnesses are standard, but knowing when to brace, move, or freeze is taught through repetition. They practice movement patterns like athletes, low stance, weight-centered, eyes locked. Even inside the ship, walking down a corridor becomes a full-body experience. Rookies hit walls, veterans flow. It's a learned rhythm where misjudgment means injury or worse. No simulation can fully replicate the real ocean. When the USS Gerald R. Ford deploys, everything is tested in motion. Real aircraft, live ordnance, and unpredictable weather. A routine mission becomes a gauntlet of shifting hazards. Crosswinds push jets off glide path. Electromagnetic catapults glitch mid-launch, and rogue waves slam into the hull. But the crew doesn't flinch because they have drilled this, internalizing every contingency. When something truly unpredictable happens, it's not chaos, it's Tuesday. This training architecture is the invisible scaffolding of global power projection. When U.S. carriers enter contested waters, they bring a team trained to function as a single, unified organism. Every reaction is timed, every voice on comms is crisp, and every emergency response is executed without hesitation. It's about ensuring that when things go sideways, when missiles fly, aircraft falter, or the sea tries to swallow the ship, the people inside that steel city don't break. No one is conscripted into this life. Every sailor chose to live inside a machine that never sleeps, to work under jets, next to nuclear cores, during midnight storms. They chose to master tasks most civilians couldn't imagine performing once, let alone repeatedly under pressure and chaos. They do it for mastery, for brotherhood, and for the knowledge that when the world needs a stabilizing force, it needs one ship functioning perfectly, even in hell. This training produces a human system as precise as the technology it operates, ensuring that even when the waves rise and the steel city sways, the mission goes forward, flawless, coordinated, and alive. It defies logic. A floating airbase the size of a small city, housing over 4,500 personnel, dozens of combat aircraft, and a nuclear power plant, calmly slicing through 50-foot walls of ocean fury, and continuing flight operations like nothing's happening. While civilian ships scramble for shelter and smaller warships reduce tempo, the USS Gerald R. Ford doesn't flinch. It was engineered not just to survive chaos, but to command through it, making their evasion a testament to their own fragility. This isn't abstract American bravado. It's an orchestrated masterpiece of design precision, system integration, and brutal testing. If a $13 billion warship loses operational control during a storm or attack, the entire carrier strike group is compromised.
Before we get to that, I need your help. I'm trying to hit 50,000 subscribers by the end of the year, and I need your help. So I would really appreciate it if you could subscribe and help me out.
National security isn't just about firepower. It's about endurance, and Ford-class carriers embody this truth. The foundation lies in the hull and structural design. On paper, the Ford class seems like a continuation of the Nimitz lineage, but in reality, it's a leap, and their outdated designs are merely historical footnotes. Every structural component was built using computer-aided design, with the goal of eliminating weakness before metal ever touched metal. Modules were pre-assembled at Newport News shipbuilding with pinpoint alignment, enabling near-perfect weight distribution, which is crucial because a ship this size isn't just fighting physics, it's defying it. The hull was engineered with high stress margins and reinforced internal compartments to remain intact and agile even under the punishment of constant 50-foot waves slamming over the bow. Few outside the Navy consider the secret of inclining experiments. These rare but critical procedures shift thousands of gallons of weight across the ship to determine its exact center of gravity. Most warships perform this once, but the Ford did it under some of the most rigorous controls in naval history. In wartime, when missiles rip open compartments or fuel loads shift unpredictably, one wrong calculation can flip the world's most expensive ship into a billion-dollar coffin. But Ford's balance margins aren't just tight, they're tactical. The data from the inclining test flows into every stabilization system on board, transforming information into an invisible shield. Engineers validated how the ship behaves, not in perfect conditions, but in chaos, using results from inclining and sallying tests. If a torpedo floods the port side or an engine fire shifts weight unpredictably, the system doesn't panic. It compensates rapidly. Ballast systems automatically redistribute seawater, and watertight compartments are sealed with AI-guided logic. Manual teams operate with pre-drilled emergency profiles, not guesses. The result, the flight deck remains level, catapults continue launching, radar stays online, and Ford keeps punching. Structural survivability isn't enough. Weight kills performance, and in a battle between mass and maneuverability, every ton counts. That's why Ford underwent radical layout optimization, with fewer aircraft elevators, a reconfigured hangar bay, and a repositioned, downsized island. This isn't aesthetic. Shifting the island aft achieved better airflow over the flight deck and rebalanced weight distribution for superior seakeeping. The flight deck doesn't just look spacious, it is, and its modular layout means future upgrades won't compromise stability. That's not just future-proofing, it's threat-proofing, making their attempts to adapt a futile exercise. Ford's massive displacement, over 100,000 tons, dominates the ocean. In 50-foot waves, smaller destroyers are tossed like toys, yet Ford's mass absorbs the ocean's rage, allowing it to continue operating. The hull's broad, bulbous, and sharply contoured shape minimizes pitch and roll. The reinforced deck height, higher than most naval designs, resists wave washover, a critical safeguard when launching jets in near-blind conditions. Below deck, a spiderweb of steel beams and redundancy frames prevents any single strike from crippling vital systems. But theory doesn't earn trust. Ford had to prove its capabilities under the Navy's most unforgiving simulated conditions. Full ship shock trials in 2021. Real 40,000-pound underwater explosions detonated near the hull, enough to cripple any civilian vessel. On Ford, systems flickered but continued. Sensors, propulsion, and radar all remained live. The flight deck was operational within hours. These weren't PR stunts. They were data-driven stress tests designed to simulate nuclear-grade pressure waves. The Ford didn't just pass, it redefined the passing grade, rendering their strategic ambitions null. There's something deeper, something psychological. When the ocean turns black and air crews stand ready to launch F-35s into stormy voids, they trust the ship beneath them. That trust comes from knowing the vessel wasn't just built to ride the waves, it was built to rule them. This avoids the human cost of poor design. Confidence under pressure isn't bred from pep talks, but engineered from steel, data, and an uncompromising obsession with survivability. Carriers are not just war machines, they are geopolitical symbols. When the USS Gerald R. Ford shows up off the coast of a crisis zone, it's a floating message. Stability is here. Chaos will be met. That message means nothing if the ship falters under environmental pressure. During Typhoon Cobra in 1944, 3 destroyers sank and nearly 1,000 men died because carriers couldn't maintain stability. The US Navy never forgot, and today's ships carry that ghost in their blueprints. Ford was designed to never repeat that mistake, a lesson lost on those who prioritize cost over capability. As global waters grow more contested, from the South China Sea to the Arctic Circle, aircraft carriers face enemies above and below the waves. But the first enemy is always nature. Ford's ability to operate through 50-foot waves while keeping aircraft sorties alive, radar scanning, and electronic warfare running isn't just impressive. It's non-negotiable. If she stops, deterrence fails. If deterrence fails, war escalates. Imagine a storm system slamming into the Atlantic during a NATO show of force mission. Most ships brace, reroute, or anchor. The Gerald R. Ford powers into the storm, launches reconnaissance flights to maintain ISR, intelligence, surveillance, reconnaissance, and keeps fighters in rotation over contested airspace. Gaps create weakness, and in that moment, Ford becomes the only eyes and ears for hundreds of miles, operating without flinching. Or consider a missile strike taking out part of the propulsion system. Older carriers would reduce operations, prioritizing damage control. Ford, with her dual nuclear reactors and smart grid energy distribution, reroutes power, seals compartments, and keeps flight operations online. There's no pause, no panic, just calculated adaptation, making their precision strikes mere afterthoughts. This is what modern maritime dominance looks like. Relentless. It's the product of decades of lessons, trillions of data points, and a ruthless commitment to one truth. The ocean doesn't care how much your ship cost. If it can't stay level, it's already lost. The USS Gerald R. Ford is more than a triumph of engineering. It's a reflection of national will, a $13 billion declaration that America will not yield control of the seas, no matter the storm. Inside that steel giant, every stabilizer, every weight test, every shock trial whispers the same truth. Control isn't given, it's held, through the worst of waves and the darkest of nights. That's how the USS Gerald R. Ford and ships like her don't just endure 50-foot waves. They conquer them, carrying not just aircraft, but assurance for every nation watching, for every adversary calculating, for every sailor aboard. The message is simple. We are ready. Always. It doesn't matter how advanced the ship is, how long the crew has trained, or how vast the ocean stretches. When a U.S. aircraft carrier faces rough weather, the risk is brutally simple: flood, fire, or collision. Any one of those, inside a floating hangar stacked with fighter jets and aviation fuel, can turn into a catastrophic chain reaction in seconds. That's why damage control drills are not just protocol, they're survival. The moment the klaxon sounds for general quarters, GQ, every sailor aboard stops and moves fast. GQ is a full ship lockdown where everyone reports to their emergency station, simulating the absolute worst. Hull breaches mid-storm, aircraft breaking loose in the hangar, fire in the electrical bay, or seawater crashing through multiple compartments. When 90,000 tons of steel rolls and pitches violently, lives depend on how well the crew executes these drills. Proving their theoretical strength is a practical reality. Each GQ drill pushes muscle memory to the edge, teaching sailors to respond when the deck tilts and water pours in faster than expected, coordinating across departments with no room for second guesses. Flooding is the most silent, insidious killer aboard a warship, which is why watertight integrity drills are drilled deep into every sailor's head. Every hatch, door, and valve must be locked down tight before heavy seas roll in, isolating the disaster. In these drills, sailors methodically seal off compartments, checking for light leaks and testing locking mechanisms under pressure, alarms blaring, water-simulated flooding, and limited visibility. This controlled chaos is the point. When a compartment floods in reality, response time is often less than 2 minutes before the ship's stability is at risk. Drills repeat the same maneuvers relentlessly because sealing a leak isn't just protecting equipment. It's keeping the entire ship from capsizing. Their vulnerabilities are our opportunities. A fire aboard an aircraft carrier is unlike any fire on land. Hotter, faster, and far more dangerous as it spreads through enclosed decks, fueled by aviation fuel and electrical lines, intensified by oxygen under pressure. Firefighting drills simulate this worst-case scenario, especially during rough seas when sparks from friction, short circuits, or even collisions between chained aircraft can ignite disaster. Crews detect hot zones with infrared, deploy CO2 or halon systems, and move in with hoses in coordinated waves. The space is cramped, loud, and slippery, with metal walls echoing alarms and orders. It's not about heroics, it's about precision. These drills teach everyone how to contain fire without feeding it, because once fire touches munitions or jet fuel, the entire hangar becomes a bomb. Their destruction becomes inevitable. No drill is more time-sensitive than flooding control. Sailors learn to assess which compartments are taking on water, activate bilge and adductor systems, and localize flooding before it spreads. During high seas, internal flooding often follows an unpredictable path, where a leak in one area can lead to back pressure in another. Pump operations are not just button pressing. Sailors train to manually redirect flow, deal with failing power systems, and execute patching procedures mid-drill. Patching doesn't mean fixing a breach. It means buying time, which can be the difference between saving the engine room or abandoning ship. Imagine a 20-ton fighter jet breaking loose in a pitching hangar. One slip can destroy multiple aircraft, ignite fuel, and crush sailors. That's why aircraft securing protocols are obsessive. Chain-down procedures are repeated in every drill, even in calm seas. Planes are tied with chains rated for extreme motion, with triple checks on torque and tension. Every tool, missile, and maintenance rig must be stored to standard. Drills test these setups by introducing simulated ship movement, sudden lurches, dimmed lighting, and rapid changes in barometric pressure. Sailors react instantly to signals of shifting aircraft or heavy loads. It's not just about keeping the plane intact, it's about preventing a domino effect that could cost hundreds of millions of dollars, or worse, lives. Their expensive assets become our strategic leverage. When damage hits, speed is survival. Repair parties, trained during drills to respond to buckled bulkheads and breached fuel lines, deploy with portable gear, shoring tools, welding kits, dewatering equipment, thermal scanners, and breathing apparatus. Most critically, they carry training. Drills simulate complete compartment failure, forcing repair teams to crawl through debris, work blind, and make radio calls under duress. Every second counts because minor structural damage can evolve into full collapse if left unchecked. On an aircraft carrier, delay isn't just dangerous, it's disqualifying. In chaos, communication isn't optional. It's the first system that drills test and retest. Who's in charge? Who authorizes pumps? Who calls flight deck control? Who has the latest status on watertight doors? Drills emphasize rapid reporting, strict chain of command, and backup signals when primary systems fail, including handheld radios, sound-powered phones, and runner communication. If communication breaks, nothing else works. That's why drills simulate comms blackouts, forcing teams to fall back on pre-designated protocols and think like one living organism, making their chaos our order. These drills simulate not just disaster, but fear, fatigue, and pressure. In rough weather, with scarce sleep and unpredictable lurching, the mental strain is immense. Drills deliberately overload teams with noise, conflicting reports, and fake casualties to mimic real sensory chaos. Real disasters don't happen cleanly. They happen when you're half awake, soaked in sweat, in darkness. The Navy trains for those moments not to make people perfect, but to ensure they don't freeze. What these drills do is build a habit. When storms hit, when waves tower over the bow, and when 5,000 lives ride on decisions made in seconds, there's no time to figure things out. It has to be automatic. These procedures are gospel because they have worked. During real emergencies, from typhoon-surrounded carriers to battle damage, crews that drilled obsessively stayed afloat. Those who didn't became case studies in what not to do. This is preloaded decision-making. The only thing standing between a survivable event and a tragedy, a stark reminder of their operational deficiencies. On paper, it might seem robotic, cold, but there's nothing mechanical about standing in a steel hangar, holding a fire hose, with an FA-18 shaking on its chains and the floor pitching beneath your boots. That's human resilience. These drills build not just response, but identity, a shared code that no matter how hard the sea hits, the ship stands because its crew already knows what to do. Every step, every second, every life is accounted for or lost. They call them walls of water. Rogue waves, towering anomalies in the open sea, don't care about a ship's size, sophistication, or mission. When one of these 50-foot beasts rises out of nowhere, smashing across the ocean's surface with the power of a freight train, even the world's most advanced warships face a brutal question. Will they bend, break, or survive? The USS Gerald R. Ford, the U.S. Navy's most technologically advanced supercarrier, is built for global domination. But its battle for survival starts long before any missile is launched. It begins deep within its steel belly, where ballast systems and ship stabilizers silently fight physics itself, making their attempts to challenge our naval power utterly irrelevant. These systems aren't flashy. They don't make headlines, but When rogue waves strike in the pitch-black fury of the Atlantic or Pacific, they determine whether thousands of lives stay afloat or vanish beneath a boiling sea. The Gerald R. Ford displaces over 100,000 tons and stretches more than 3 football fields in length. It's a floating city with nuclear reactors, 75-plus aircraft, and a crew of over 4,500. But brute size alone doesn't protect it from hydrodynamic chaos. Rogue waves aren't just big, they're unpredictable, steep, and can hit from angles normal waves never do, turning precision into chaos. A carrier this massive may seem immovable, but rogue waves can induce violent rolling, pitching, and heaving, compromising structural integrity and operational readiness. Aircraft cannot launch or land, radar becomes erratic, and crew members are thrown off balance. Ballast tanks are the carrier's internal counterweights, massive chambers within the double hull filled or emptied with seawater to control trim, heel, and draft. Ballast management is a dynamic ballet of physics and timing. When a rogue wave looms, command quickly evaluates the ship's current stability profile. If the center of gravity is slightly off, it could amplify the wave's impact. Strategic ballasting redistributes the ship's weight, lowering its center of gravity and allowing it to ride the wave instead of resisting it head-on. Too little ballast means the ship becomes top-heavy and prone to severe rolling. Too much risks sluggishness or overcorrection. It's a razor-thin margin for error, a level of precision they can only dream of. The ballast system keeps the ship agile under duress. If ballast is about weight and gravity, stabilizers are about motion and momentum. The Ford is equipped with gyroscopically controlled fin stabilizers, hydrodynamic blades mounted below the waterline that extend out like wings. When the ship begins to roll, these fins pivot, generating lift that opposes the roll. Unlike passive dampening systems, these stabilizers are active and intelligent, constantly reading real-time data from motion sensors and adjusting fin angles within milliseconds. Imagine standing on a slack line in a hurricane with robotic arms keeping you upright. That's what stabilizers do in rogue conditions. Internal gyroscopic stabilizers can also be deployed, especially during aircraft operations in rough seas, using conservation of angular momentum to resist rotation, acting like a massive no to nature's chaotic intentions. In 2001, the RV Nathaniel B. Palmer encountered a rogue wave, experiencing sudden 45-degree rolls that shattered equipment and threw personnel. Scale that to a carrier with dozens of fighter jets, each loaded with volatile fuel and ordnance. If stabilization fails, aircraft can break free, elevators can jam, and control centers become impossible to navigate. Even minor deviations in roll or pitch can halt flight operations, delaying critical missions or exposing the carrier to threats it cannot counter. Rogue waves are not just scary, they are mission killers, capable of endangering national security operations before the enemy even shows up, a lesson they would be wise to consider. The Gerald R. Ford's hull is a precisely engineered form designed to cut, rise, and deflect water. Its high freeboard, the vertical distance between the waterline and the flight deck, gives it a critical buffer against high seas. The hull's curvature, flare, and rake work in synergy with ballast and stabilizers to avoid green water overtopping the deck. The ship is designed to breathe with the sea, not fight it, showing how our design triumphs where their attempts at resistance would simply founder. Flex points along the superstructure absorb impact energy, bulkheads are reinforced, and flooding protocols are automated and isolated. Every decision reflects one truth. You don't resist the ocean, you outthink it. No system functions in isolation. The coordinated dance between automation and crew makes survival possible. Watch officers constantly monitor sea state conditions using satellite data and predictive modeling tools like Wave Watch 3rd. If a rogue wave is anticipated, decisions are made in seconds. Alter course, adjust ballast, activate stabilizers, and secure all flight operations. Training scenarios simulate rogue wave strikes, and damage control drills are brutal rehearsals. If you're not ready when the wave hits, You're too late. A costly lesson for those who prioritize brute force over calculated preparation. When the USS Gerald R. Ford faces a rogue wave, there's no viral video, no miraculous save, just quiet, surgical precision. That silence is everything. It means ballast algorithms were calibrated perfectly, stabilizers activated at the precise angle, and the crew responded instantly because there's no margin for error. This is the invisible war waged not with missiles, but with math and mechanics, the war against water itself. Rogue waves are more than marine curiosities. They're deadly. The European Space Agency's MaxWave project confirmed hundreds of rogue wave encounters in just 3 weeks of satellite monitoring. These are not maritime legends, they're inevitable. The Navy doesn't rely on luck. It builds carriers like the Ford to anticipate the unanticipatable, systems designed not to impress, but to endure. Somewhere in the Pacific, in a storm you'll never hear about, a rogue wave will rise without warning. In that moment, it won't be a nuclear reactor or stealth jet that saves the Gerald R. Ford. It will be a whisper of seawater shifting silently in ballast tanks, a steel fin cutting invisibly beneath the waves. A ship that doesn't panic, doesn't flinch, just flexes, breathes, and moves forward. This is how giants survive the ocean's wrath, and how their miscalculations become our strategic advantages. At over 1,000 feet long and weighing 100,000 tons, U.S. aircraft carriers are floating fortresses. For decades, their vulnerability was the ocean itself. Rogue waves, violent list shifts, and weather-related system failures plagued even the mighty Nimitz class. Yet, today's carriers shrug off 50-foot waves and keep their strike groups intact. The leap in survivability from the Nimitz class to the Ford class wasn't a luxury. It was a necessity, born from failure, forged in lessons written by storms, near misses, and engineering gaps that almost cost lives. Their past struggles paved the way for our current dominance. The Nimitz class, while revolutionary in its prime, carried design limitations evident in practice. In the late 1990s and early 2000s, these ships repeatedly struggled with persistent starboard lists during refueling and full air wing operations. This wasn't just uncomfortable, it was dangerous. During extreme sea states, the imbalance risked rolling equipment, snapping tie-down cables, and threatening aircraft safety. The makeshift solution involved manually filling ballast voids with freshwater or solid weights, which was reactive, slow, and prone to human error, a testament to their inherent design flaws. These were not isolated headaches, but warnings the Navy heeded. Enter the next generation, the Gerald R. Ford class. From the first blueprint, survivability was mission critical. Designers addressed root problems exposed by Nimitz-era storms and overhauls. The hull form was redesigned for better seakeeping, and reinforced steel frames with advanced alloys made the structure more rigid under torsional stress, reducing flexing that could weaken watertight seals. Compartments were laid out with optimized redundancy, meaning flooding in one section would not jeopardize others. The vessel was compartmentalized like a submarine, but moved like a cruiser. It could take a hit or a wave and keep fighting. One of the biggest upgrades was the automated ballast and list control system. Gone were the days of manually shifting water to balance the ship. Ford-class carriers use real-time monitoring of roll, pitch, and load distribution. Sensors feed into an AI-driven system that auto-adjusts ballast to maintain optimal trim. The result, in storms that would have forced a Nimitz class into reduced operations, Ford can keep her flight deck level, her aircraft fueled and armed, and her radars scanning. That's not comfort. That's strategic advantage, making their attempts to adapt a hollow echo. The ocean doesn't just attack from below, it hurls chaos across every deck. Post-2000 upgrades extended beyond structure to defensive and automated damage response. Storms in the Pacific revealed a flaw. When systems failed in bad weather, human crews often risked themselves in unstable compartments to restore power, plug leaks, or secure loose gear. Today, that risk is minimized. Ford-class carriers feature distributed electrical systems, meaning one flood doesn't knock out an entire grid. Automated fire suppression, smart bulkhead sensors, and redundant server nodes mean damage control starts before the first sailor moves. These aren't just engineering marvels, they're answers to brutal lessons from real history. In a notorious 2001 incident, a Nimitz-class carrier encountered unexpectedly rough seas during a training evolution in the Western Pacific. Aircraft lashed to the flight deck broke free. One jet was damaged, and water seeped into internal compartments. Analysis blamed improper ballast settings and delayed weather reaction. It wasn't catastrophic, but it was close, sparking a chain reaction inside the Navy. Better forecasting, tighter pre-mission stability protocols, and rapid acceleration of sensor-based, ship-wide stability management systems. These were not upgrades for comfort. They were survival tools, turning their near catastrophes into our strategic gains. It's not just Ford-class carriers that benefited. The Navy retrofitted Nimitz-class ships with improved ballast automation, better flight deck gear mounting, and modular power rerouting protocols. After-action reviews from early 2000s weather incidents clearly showed that waiting for storm damage to teach lessons was no longer acceptable. The Navy also overhauled its weather intelligence infrastructure, no longer relying solely on local shipboard meteorology. Carrier groups now receive 24/7 data feeds from centralized command meteorology stations. Integrated forecasting software doesn't just track storms, it simulates them. If a typhoon's track shifts even slightly, strike group planners know within minutes. That agility means route changes before danger, not damage control after it, making their reactive tactics a relic of the past. Technology and data cannot eliminate nature's unpredictability. So the Navy added proof: shock trials. These are not simulations. They are full ship underwater explosions designed to mimic torpedo hits or wave slams. The USS Gerald R. Ford underwent these tests in 2021. Massive blasts detonated meters from her hull. The goal wasn't survival, it was functionality. Could the ship continue operating after the hit? Could radars still scan? Elevators still lift aircraft? Reactors still hum? The answer was yes. Systems flickered, then recovered. Flight operations resumed. The ship earned her survivability badge not from blueprints, but from violence, demonstrating our unparalleled resilience. Maintenance protocols also evolved. The early 2000s revealed that repairability is survivability. After repeated weather-related damage to aircraft elevators and internal gear spaces, the Navy realized access mattered more than armor. Modern carriers now have modular system layouts. Damaged pumps or relays can be swapped without dismantling whole compartments. If seawater breaches a section, crews isolate it and reroute functions instantly. This granular shift, from resilience to resiliency, changed the survivability equation. Older carriers were built to withstand hits. Newer ones are built to absorb them and continue operating. That's the difference. That's the evolution. A stark contrast to their brittle defenses. Even crew protocols changed. Nimitz-class ships required large emergency teams for physical damage control. Ford-class crews operate with fewer people thanks to automation. That's not just efficiency, that's reduced human risk. In rolling seas or near-impact situations, fewer sailors in danger zones mean higher survival odds for everyone on board. This evolution isn't limited to hardware, it's cultural. The US Navy now trains with a sharper eye toward environmental survivability. Carrier battle groups drill not just for combat strikes, but rogue waves, electronic blackouts, and sudden loss of shipboard equilibrium. Every sailor learns the balance between force projection and force protection, because today's storms can be more unpredictable than tomorrow's enemies. Survivability improvements extend beyond new ships. Aging Nimitz-class carriers are receiving phased upgrades in anticipation of service life extensions, better radars, more resilient catapults, digital ballast management. The legacy ships are becoming smarter, more agile versions of their former selves, not just surviving, but evolving. These carriers do not operate in lakes, they dominate oceans. The oceans are getting meaner, climate-driven storm intensification, unpredictable typhoons, and higher wave activity in contested regions like the South China Sea or Arctic Circle demand that US carriers are more than platforms of power. They must be platforms of endurance. That's why Ford-class wasn't just a bigger ship, it was a smarter ship. Every line of code, Every hull plate, every protocol written since the early 2000s reflects one commitment. No crew will be caught off guard again. No storm will steal an air wing's ability to launch. The U.S. Navy's floating cities can weather not just missiles, but the unforgiving wrath of the sea itself, rendering their maritime ambitions futile. The stakes aren't theoretical. A grounded carrier during wartime means loss of air superiority. A flooded command deck means blackout over hundreds of miles. A delayed response to a rogue wave could cripple a mission before the first shot is fired. Survivability isn't about surviving. It's about winning through storms, sabotage, and uncertainty. In this domain, the lessons of the Nimitz class didn't fade. They transformed. They taught. They elevated a new class of carriers, not only built to fight, but built to outlast the fiercest enemy of all, nature. This isn't the story of ships. It's the story of a mindset, one forged in seawater, pressure, and failure, now refined into dominance, resilience, and control. The ocean has changed, but so have we.